Welcome to this FMSP online revision video for OCR FP3 looking at the topic of differential equations. We'll start by looking through the specification statements and then we'll take a look at some exam questions on this topic. So, going through the specifications to begin with, what you need to know is how to find an integrating factor for a first order linear differential equation and use this integrating factor to find the general solution. We'll take a look at that in a bit more detail in a second. Then you should be able to extend the work you've been doing in Core 3, Core 4 to use a given substitution, and note that you will be given the substitution in this case, to reduce a first order differential equation to linear form or form in which the variables are separable. So you will be given the substitution and you just need to apply that to turn it into a straightforward differential equation. Then, and it's often in the case when you're working with second order differential equations, you should be able to know what a complementary function means. That's when your differential equation is set equal to 0, and a particular integral, which is a solution of the differential equation when the right hand side is not 0, and use that to be able to solve a first or second order linear differential equation. And in practice you should be able to do that. Find the complementary function for first or second order linear differential equation. For the particular integral, this is where the right hand side of a differential equation will have some form, either a linear term in x, or an exponential, or a trig function, and you set the right hand side equal to one of these forms and use that to find the particular integral. We'll have a look at that at an exam question in a minute. And then finally, with any differential equation, be able to use initial conditions to find particular solutions. In other words, to find the values of the constants, which may be plus c, as they would be with a standard A-level maths type integral, or it may be the constant is a multiplier. Now, we mentioned integrating factors a moment ago, and you're expected to know this, which is not in the formula book. And this is that if you have a differential equation of the form dy by dx plus a function of x times y is equal to a function of x, then the integrating factor is e to the integral of the function that's being multiplied by y here. This, as you'll see in a minute, turns it into something which is effectively the result of applying the product rule for differentiation. The other thing to watch out for is if you have a multiplier here on the front, you have to divide through before we can apply this method. So let's take a look at some exam questions that cover all of those things. The first of them is an integrating factor question. So, reading through the question to begin with, you're told to use the integrating factor method to find the solution of the differential equation dy by dx plus 2y is e to the minus 3x. And you need to find the solution for which when y is 1, x is 0, and finally give your answer in the form y equals f of x. So, our integrating factor starts off, well, we don't have a product here, so we can go straight into our method because we just have a function of x times y. Our function of x here is quite simple, it's just 2. So we can immediately say that our integrating factor is e to the integral of this function that's been multiplied by y, which is 2 dx. Integrate 2 with respect to x and we get e to the 2x. So now we can apply our integrating factor, in other words multiply by this e to the 2x, and we get e to the 2x times by dy by dx is equal to 2 plus 2e to the 2x y is equal to e to the 2x times by e to the minus 3x. Now if this has worked, this should look like the product rule, which it does. I've got this thing times the derivative of y, and then I've got the derivative of this thing times y, which basically looks like the result of the product rule. So that whole thing is effectively differentiating e to the 2x times by y. And this is my u dv dx plus v du dx, if that's my product. My right hand side, e to the 2x times e to the minus 3x, is e to the minus x. Now I can integrate. Integrating the left hand side just leaves me with e to the 2x times y, and integrating, I get the integral of the right hand side, which is going to be minus e to the minus x plus c. Now we're almost there with this one. We just now need to find what happens if y is 1 when x is 0, and then give our answer in the form y equals f of x. So first thing is to sub in y is 1 when x is 0, e to the 0 is 1, so I've got 1 times 1 on the left hand side, 1 equals minus 1, minus e to the 0 is minus 1 plus c, and that leaves me c equals 2. And finally I just need to write out this whole thing as a y equals, so I get y equals, divide through by e to the 2x, minus e to the minus x over e to the 2x is minus e to the minus 3x plus 2 over e to the 2x. And there we're finished. 6-mark question. Let's have a quick look at how the marks are awarded with this. So you would actually get a straightforward mark here, a statement mark for this e to the 2x. You would then get a method mark and an answer mark for applying the integrating factor correctly here, and then an accuracy mark for the integration itself, a method mark for the substitution, and another accuracy mark for the correct value of 2, and then a final accuracy mark, an easy one to miss, but it does say expressing the form y equals f of x here for writing it out with y on the left hand side. So that's the integrating factor method. One thing we've not seen in this question but you should be aware of is, as I say, if there was a multiplier on the front here, say there was an x squared on the start to begin with, you would just divide through all your terms till you were just left with a dy by dx here, function of x times y and a function of x on the right hand side, and then apply the integrating factor rule. So let's take a look at a substitution based question then. So here, and again it's good practice to read through a question before you start it, you're asked to use the substitution y equals xz to find the general solution of the differential equation x dy by dx minus y equals x cos y over x, giving your answer in a form without logarithms, and you're told you can use an appropriate result given in the list of formulae. Secondly, you're asked to find the solution of the differential equation for which y equals pi when x equals 4. So let's see if we can make a start on this question then. So first thing to do is use y equals x over z in here. Now if we're going to use y equals xz, we need to know the derivative of here. If I differentiate through by x, I get dy by dx equals, and then I've got product rule again here, u dv dx x dz dx plus v du dx z times by 1, and that gives me a form of dy by dx in terms of dz by dx just by applying the product rule there. I can then substitute in this and this into my statement here, and that's going to give me x times dy by dx is x times by x dz dx plus z minus y minus xz is equal to x cos y over x is the same as z if we look here. And so you see here, this is exactly as we said, if you're going to be expected to do a substitution, you'll be given it, and we've been given it here. Now we're not quite in a position yet to integrate to solve our differential equation, so we need to do a bit of collecting together of terms here. I'm going to have x squared dz by dx. I'm then going to have xz minus xz, which will cancel. Xz minus xz will cancel, and my right hand side now becomes x cos z. What I can do then is separate my variables to give me divide through by cos z. I get 1 over cos z or sec z, integral of sec z dz, and separating my variables on the right hand side, x over x squared is 1 over x. I get integral of 1 over x dx. So now it was just turned into a separation of variables, separated my variables. I should now be able to integrate this, and we're told we may quote an appropriate result given in the list of formulae. And these here are the two alternative versions. This is integral of sec x dx here from the formula book. So I'm going to go for the first one of those. So I'm going to say that the log of sec z plus tan z is equal to integral of 1 over x is ln x plus c. And finally then a little bit of rearrangement, a little bit of collecting together. If I take e to the power of both sides to get rid of my natural logs and replace my z's with a y over x, I'm going to have sec y over x plus tan y over x e to the ln x plus c. You should be comfortable with that. What happens with the c there, that's effectively e to the c times e to the ln x can be replaced with an a, and I'm going to get a x. So that's the first part of the question. In the second part, we're asked to find the solution to the differential equation for which y equals pi when x equals 4. So just to remind us what we had sec y over x plus tan y over x was equal to ax. And again, it's just a case of substituting in and solving here for the a. So I'm going to have sec of pi over 4 plus tan pi over 4 is equal to 4a. I should now be able to solve this for a. Cos pi over 4, 45 degrees. Cos 45 degrees is 1 over root 2. 1 over root 2 is root 2. Tan 45 degrees is 1. So this equals 4a. So a is root 2 plus 1 over 4. And my solution is therefore sec y over x plus tan y over x is equal to root 2 plus 1 over 4x. Note here we haven't been asked to give this in the form y equals x, which is good because that would be incredibly complicated. So let's take a quick look at the marks awarded for this question then. So in the first part here there's a method mark, a statement mark for getting this form of the substitution, the derivative of the substitution, which is needed to apply the substitution. A method mark then for substituting in, and an accuracy mark for getting the correct integral. There's then a method mark for applying that integral and getting an appropriate term from the formula book, and an accuracy mark for getting that whole thing correct, and then a final accuracy mark at the end there for this thing I was talking about, that the e to the ln x plus c rearranges to a constant times x. For the second part of the question, just 2 marks available here. The first one is a method mark for evidence of a correct substitution, and then finally, as you would expect, an accuracy mark for the correct answer. So we'll finish off by looking at a second order differential equation. So in this question, you've been given a second order differential equation, 3d squared y by dx squared plus 5dy by dx minus 2y equals minus 2x plus 13. We're asked to find the general solution of that, then find the particular solution for which y is negative 7 over 2 and dy by dx is 0 when x is 0, and then a final 1 marker here, write down the function to which this would approximate if x was large and positive. So let's start off then by saying we're going to find our complementary function by solving when this is equal to 0, and we're going to start with an auxiliary equation in part 1 here. So I'm going to start by solving the auxiliary equation, which is the equivalent quadratic equation to this differential equation, which is 3 lots of the squared term, 3 lambda squared, plus 5 lots of the constant term, minus 2 equals 0. And this should be a quadratic equation that's fairly easy to solve. You would expect it to, you're going to hope it either factorizes, or if not, gives some complex numbers, but 3, 5 and 2 look fairly promising, and 3 lambda and lambda. Minus 2 is going to be minus 2 and plus 1, or plus 2 and minus 1. Well, plus 2 here and minus 1 there gives me 3 2s are 6, minus 1 is positive 5, and that's factorized. So our solutions then are lambda equals a third, or lambda equals negative 2, and they then give me my powers of e in my complementary function. Y equals a e to the third x plus b e to the negative 2x. And that would be the solution to this second order differential equation if the right hand side was 0, and that's known as our complementary function. You should also, and please take note to practice these, you should know what to do with the repeated solution, where we get something like, if it was lambda is 2 and lambda is 2, ax e to the 2x plus be to the 2x, and also what to do if you get complex numbers here, and they give you, your real term gives you your power of e, and your imaginary term gives you your constant with cos ax and plus sine bx. So you do need to practice those, and do look at some other questions from the textbook or past papers where you've got roots that are either repeated or complex, but here they're quite straightforward, they're real and distinct, and we can go straight into this form of the complementary function. So now we're looking for the particular interval, which is, we've solved what would happen if this was equal to 0. We now want a solution in the case whereby the right hand side equals minus 2x plus 13. Just get a bit more space for this. So we know that a particular interval, now the right hand side here looks linear, so the particular integral will also look linear. If it had been an e to the x type term, you'd have tried an e to the x type term. If it had been sine or cos, you'd have tried sine x plus cos x type function. So if y is cx plus d, dy by dx is c, and the second derivative d2y by dx squared is 0. Substituting those three in, I get 3 lots of 0, which can be ignored, 5 lots of c, minus 2 lots of cx plus d is equal to minus 2x plus 13. To get, looking at my coefficients of x, on the right hand side I've got minus 2, on the left hand side I've got minus 2c, so minus 2c equals minus 2, c equals 1. Substituting in c equals 1, looking at the constant terms, I've got 5c, 5 times 1, minus 2d, and a constant term of 13 here, equals 13, and that gives me d equals negative 4. 5 minus 2 times minus 4, 5 plus 8 is 13. Therefore, my particular integral is x minus 4. And so I can just finish this off now by writing out my solution, which is y equals ae to the third x plus be to the minus 2x plus x minus 4. Now we're then asked to find the particular solution for which y equals negative 7 over 2 and dy by dx when x equals 0. Well, looking back here, I can see that if y is negative 7 over 2 when x is 0, let me just copy this out the top here so I know what I'm working with. This is my solution. So if y is negative 7 over 2, then my left hand side is negative 7 over 2, and my right hand side is a e to the naught is 1, a b e to the naught is 1, x is 0, minus 4. My dy by dx, if I differentiated this, well, dy by dx is 0 for this particular solution. Differentiating here, I get a third ae to the third x, and ae to the third x is 1 when x is 0, minus 2b e to the minus 2x, which is 1 when x is 0. Differentiating here, I get plus 1. And now I just need to solve these two simultaneously. So looking at this here and multiplying through by 2, I get 2a plus 2b minus 8, and I can add on the 7, and I can take off the add on the 8, and I get 1 equals 2a plus 2b. There's a variety of ways you can solve these simultaneous equations. Similarly, multiplying, taking the 1 over to this side, I get minus 1 equals a third a minus 2b. Add those together, and I get 0 equals 7 over 3a, which tells me a is 0. And if a is 0, then I get 1 equals 2b, so b is a half. And my particular solution here then is y equals, don't need the a term, a half e to the minus 2x plus x minus 4. And finally, for the third mark, write down the function to which y approximates when x is large and positive. Well, if x is large and positive, this term will become very, very small. So we can say y tends to x minus 4 when x is large and positive. Quick look at the mark schemes for this then. In the first part there's a method mark here for identifying a correct auxiliary equation, and an accuracy mark for the two correct roots of this, and then a further accuracy mark for the complementary function. There's then a method mark for solving your for using the correct form of a particular integral. Accuracy marks for getting each of the terms C and D, and then a final accuracy mark there, the 7th mark, for the full general solution written out. In part 2, for the particular solution, there's a method mark for each of the 2 equations that you're going to solve simultaneously based on substituting in y is -7/2 and dy by dx is 0 when x is 0. A method mark for solving those simultaneously, an accuracy mark for the values, and then a final accuracy mark for the answer, and then 1 mark for correctly identifying y tends to x minus 4. That's looking at questions on each of the bits of this topic for differential equations. If you want other videos for OCR, FP3 or for other units, please look on the furthermaths.org.uk website.